Okay, yes. So thank you very much, Joachim, for waiting for us. Sorry for the small delay. So here we go with the third lecture and discussion session by Joachim Brod on effective theory of performance.
Okay, very good. Welcome back. I'll leave my camera switched off because I have the feeling there will be again internet problems if I leave it on. So, but I hope you can hear me.
Yes.
Okay, very good. So I don't know how we should proceed. I have two suggestions. Like either you just ask me questions right away and I try to answer, or to get us started, I can talk a little bit more about this the chiral effective theory and the power counting and how to decide, you know, which diagrams are important and which ones are not so important, like when to include pion exchange, when not to include pion exchange, something like this. Is there?
Okay, why not? Yeah, I think it's a good idea. While we wait for the people to questions.
Okay, or we can also wait another minute until people settle down.
No, but I think most of the people who could come are now here. Let's see what they are doing.
Okay. Okay, let's start. So if there are no questions, then let's discuss a little bit this power counting in the chiral effective theory. So what we have seen is, so what is, let me maybe back up a little bit and say, what is this chiral effective theory? So we have seen that at low energies, QCD is non-perturbative. So we cannot do an expansion in alpha S, in the strong coupling. That works at high energies for the LHC. And it works very well in QED, but it doesn't work at low energies for QCD because the coupling runs and it becomes large and the series just doesn't converge anymore. So what we did as a strategy instead is we looked at the symmetries of QCD, and well, we have Lorentz symmetry, we have the QCD gauge symmetry, and we have the chiral symmetry, and we have parity, and so on, barrier number conservation, and so on. And then we try to find an effective theory that is expressed in terms of the low energy degrees of freedom, pions and nucleons, that has exactly the same symmetries. Okay, forget about gauge symmetry, that was wrong, but all the other symmetries, the global symmetries should be the same. And then we wrote down this chiral Lagrangian, and we have seen that it came with derivatives. So the leading term already had derivatives. So the leading term was, let me write it down again, something like pion decay constant squared divided by 4, and then trace over the derivatives of these exponentials of the pion matrix, something like this. Plus dot, dot, dot. And you can, so this is the only, you know, chirally invariant term with two derivatives. And if you want to include more terms, they will have more derivatives. So what you see, this is now not an expansion in a coupling. This is an expansion in derivatives. And you know that derivatives correspond to small momenta. And they correspond to momenta. And in our case, these momenta are small. They're just the momentum transfer in the scattering process. So the expansion is effectively something like Q squared over M squared, where M is the nucleon mass or the dark matter mass. So that's kind of our expansion. And then you can write down similar terms. You know, we wrote down more terms that include the masses for the pions, that include interactions of pions with dark matter, and we also included the interactions of nucleons with pions and nucleons with dark matter. So there are many more terms here. And now the question is, and now you can start drawing Feynman diagrams. Okay, so the ingredients are now the nucleon lines, dark matter lines, and pions that can be exchanged in some way. And the question is, which of these diagrams should you include? Because, okay, if there's a small coupling, it's clear, we know what to do. We include the tree-level diagrams, but if we have this chiral expansion, is it clear that we also should include, that we should start with tree-level diagrams? And that's what I wanted to discuss a little bit. So since this is an expansion in Q squared over M squared, so let me write this actually as capital Q by convention. What we need to do is if we have given a diagram, we need to calculate this power of this suppression. So let me write this more generally as Q over M to some power nu. And how do we calculate nu? So nu is somehow given in terms of the diagram. Okay, and for this we just need to count the powers of momentum in each ingredient of the Feynman diagram. So, for example, each pion propagator goes. Let's treat pions for the moment as massless. So this goes just like 1 over Q squared. It's just the pion propagator. Then for each closed loop in the diagram, we have an integration. So each, let's say, closed loop contributes another factor of, so there's a 4-dimensional integration. So this contributes a factor Q to the 4. Okay, and then we have seen that our interaction vertices, they come with derivatives. So depending on how many, so each derivative gives you another factor of Q over M. So each derivative counts like Q. Okay, so now we just need to add everything up. So this power nu is given by, okay, you have to look at all the different vertices that you have, sum over all the vertices. And each vertex, so vertex type V, comes with a certain number of derivatives. So that's number of derivatives, di. Each one contributes a factor Q. Then each pion propagator gives a factor -2. So -2 I is just internal lines. And for now, let's just look at only pions, only pion diagrams. And then each loop integration gives a factor 4. So we get this formula. Okay, this now is not so nice because it depends on, on the specifics of this diagram. So it's kind of hard to use this formula. You need to count the internal lines and so on. But there's a trick to rewrite this formula a little bit. And the trick is the following. There's a nice formula. If you have a planar graph, then there's a relation between the number of internal lines, the number of vertices, and the number of faces or closed loops. And this relation is that the number of faces minus the number of internal lines plus the number of vertices is always 1. It's constant. Okay, if you want, you can try to prove this formula. It's maybe fun to find the proof for this. But if we use this relation, if we insert this relation into this formula for nu, we find that nu is given. So we can eliminate this dependence on the number of internal lines, and then we find that nu is just given as sum over I, vi, di -2 plus 2L plus 2. Okay, so we eliminated this this I. Okay, and that's now very nice because that just depends on the type of vertices that you have, so the type of interactions that you're looking at, and the number of loops. And the leading piece, of course, for the leading piece, you want to minimize nu, so you want to have the least suppression. And if you're given certain interactions, you see already that you get the minimum nu if L equals 0, so the tree-level diagrams. Okay. Does it make sense?
Yes.
Okay. Okay. No protest. Okay, good. So that was only pions. So let's generalize this a little bit. So the first thing that we So the next thing that we want to do is we want to include nucleons. So nucleon lines, because we want to scatter on nucleons. So it is actually quite essential to have nucleons in the picture. Now, for nucleons, we have to be a little bit careful because we treat them as non-relativistic and they are heavy.
I actually have a quick question about pions, if that's okay.
Sure.
Sorry, I wasn't fast enough when you asked for questions. I think this is probably from the previous lectures, but can you remind me why we are treating pions as these kind of mediator particles in the first place?
Yes. I think I can answer this question better after we finish this discussion, but the short answer now is that in some cases, the leading interactions, like, now we will generalize this formula to include nucleons in dark matter. And then we will just see that for some interactions, the leading pieces involve pions. If you don't include the pions, you don't get the leading interactions. You get something that is much more suppressed, and that gives you just the wrong picture of what's happening. Okay, and this typically happens if you have like pseudoscalar or axial vector interactions. Like anything that is odd under parity will couple to single pions, and in this case, typically a pion exchange will be the leading term.
Okay, and is that related to the spin of the pions?
It's related. I think so. The pion is in some sense. So the pion is a spin zero particle. So it's a scalar, but it's a pseudoscalar in the sense that it has intrinsic odd parity. So it's related to the odd parity of the pion.
Got it. Okay, thank you.
Yeah, sure. Okay, yeah. So let's continue, and then we'll see the more detailed answer to the question. So we now want to do the same thing, the same counting. So we want to count like by how many powers of momentum the nucleons are suppressed. For this, we need the nucleon propagator. And so nucleon is a fermion, spin 1/2 fermions, and the propagator looks something like this. P slash plus Q slash plus M nucleon divided by P plus Q squared minus M nucleon squared. And so what is this? So P is kind of the nucleon momentum, and Q is some kind of pion momentum. So, if you have a nucleon line and then there's some interaction with a pion, there will be a momentum P here and then a momentum Q coming in here. So there will be a momentum P plus Q going here. Okay, so if there's pion interaction, so the general form of the propagator will be something like P plus Q is the momentum going through. So that's this P plus Q that's here. So that's the nucleon. That's the pion part of the momentum. So now the nucleon momentum has always this large, so we didn't do any rescaling here, so it has always this large mass piece, whereas the pion momentum is always small. So we want to essentially count the powers of the pion momentum. And so we write this as, we take the limit that Q becomes small, and then we take the leading piece. So if we look first at the denominator, so P squared, okay, so this is P squared plus 2P dot Q plus Q squared. P squared is actually just M nucleon squared. Yeah, it's just the for momentum squared, that's M nucleon squared. You see this one and this piece cancels. The Q squared piece is more suppressed than the term linear in Q. So the denominator just goes like 2P dot Q. And in the numerator, we can just neglect this Q slash piece. So that goes like minus I P slash plus M nucleon. Okay, so in the low energy limit, that's how the nucleon propagator goes. And just out of curiosity, this actually, so this Mn, that's just Mn in some sense is just P0. It's just the momentum of the energy of the nucleon in the low energy limit. So you see this thing is proportional actually, is proportional again to this 1 plus V//2 projector. So it's kind of consistent with what we did before. But that's just a side remark. Okay, so very good. So what do we learn from this? We learn from this that the nucleon line scales like 1/q. A nucleon propagator scales like 1/q. Okay, so we generalize our formula. So now nu is given by sum over I vi di. So that's just again the number of derivatives in the interaction vertices between nucleons and pions, or between pions. And then let's just add another term d chi, and that's the number of derivatives in the interactions with the dark matter current. Since we always have only one dark matter particle going in and out, there's just one of these interactions. So let's just separate this out. Okay, so that's all the pion nucleon stuff, QCD stuff, let's say, and that's the dark matter interactions. Just count the number of derivatives. Each one gives a factor of q. Then, as before, we have each pion propagator gives factor -2, power -2. Then, as we have just seen, each nucleon line gives a factor 1/q, so -in. So that's the number of nucleon lines. And then each loop integration gives a factor 4. And that's it. Okay. So that's the most general power counting formula for the suppression of the diagrams. Again, now this is not in a useful form because it depends on this number of internal lines, and that's kind of complicated to deal with. But we can again use this Euler formula that relates the faces, the edges, and the corners of a graph. So L minus number of pion lines minus number of nucleon lines plus number of vertices equals 1. That's exactly what we had before. That's just a constant, that is 1. And then we can use another relation. And the other relation is that the number of nucleon lines is constant. So each nucleon that goes in will also come out. And that's just a consequence of the fact that we treat them as non-relativistic. They're heavy and non-relativistic, and there's not enough energy to create any nucleon pairs or nucleon antinucleon pairs. Okay, so we have another relation, which is given by 2 times the number of internal lines plus the number of external nucleon lines is just given by number of derivative, okay, given by the number of nucleon vertices. So essentially what this is saying is, each external nucleon line either ends in a vertex with a pion, or it goes just through the diagram, okay? There's no nucleon line vanishing. Okay, so if we insert these 2 relations into our formula above, this becomes, and then, okay, let's do one more thing. No, okay, let's do first this. Let's do this in 2 steps. Okay, so we get the following nu. We can write this as sum over I, vi, number of derivatives, plus ni over 2 minus 2. So this Ni is just the number of nucleon lines in each vertex. Plus 2L minus number of external lines plus 2 plus d chi. Okay, so now again we eliminated the dependence on this number of internal propagators, and it just depends on the type of interactions, how many derivatives, how many nucleon lines, on the number of loops, and on the number of external nucleons. Okay, and then, okay, so that's essentially the final formula. One can rewrite this a little bit by recognizing that this topological formula here is it's valid for each connected component. So each connected component will have like a constant sum of faces, edges, and corners equal to 1. So if you have C connected components, this 1 will just be replaced by C, capital C. So we can write this also as in a different form as 4 minus A okay, one more thing. Okay, so connect the components, and then each, as I said, each nucleon line that goes in must also come out. So you can just replace this En over 2 by the number of nucleon lines. So like a nucleon line has one nucleon coming in and one nucleon coming out. So I write this just as A, and then I get 4 minus A minus 2 times number of connected components plus 2L number of loops plus this term that characterizes the interactions. I plus Ni over 2 minus 2 plus d chi.
I have a quick question.
Yes.
I didn't quite get your argument about topology and that C value and where that comes from. Could you repeat that, please?
Yeah, so, okay, first of all, is it clear where this formula comes from?
I think so, yes.
Yeah, so that's just from like counting, like looking at each piece of a given diagram and counting with how many powers of momentum it comes, and just adding everything up. And so that formula is already correct, but it's not very useful because, you know, it's kind of very specific to a given diagram because it depends on how many internal lines there are. But one can modify this formula a little bit by recognizing that these variables here, they're not all independent. So the number of vertices, the number of lines, and the number of faces, they satisfy a relation, which is this relation. Okay. Plus, since the number of nucleons is conserved, there's also a relation between, you know, internal nucleon lines, external nucleon lines, and number of nucleon lines in each vertex. That's conserved because number of nucleons is conserved. Okay, so we have these two additional relations, and we just plug them in here, and that's essentially how we get here. Okay, that's, in some sense, it's the same formula that we started with, but it's in a slightly more useful form because now it doesn't depend so much on the internal details of the diagrams. You see, essentially, this dependence on the internal details was kind of spurious. And really what it just depends on is how many loops you have and how many nucleon interactions you have and how many derivatives you have.
And how do we get C?
How do I get A? A is just A?
Sorry, C.
C. C is, so that's for one connected. 1 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 component. And for C connected components, you have just C times this formula. So you would have equals C. Like each connected component, you know, if a diagram separates into two pieces, then like each individual piece will satisfy this relation. So if you have a diagram that looks like this, or a diagram that has another piece, just something like this, I don't know, then each of these individual pieces will satisfy this relation. So I can just sum over the pieces, and the sum gives C. Does it make sense?
And those are two separate diagrams that you just drew? Sorry.
Yeah, and some, I mean, this is maybe a stupid example that, okay, maybe a more, think of, you know, if you think of, maybe it's better to think in terms of nucleon lines. If you scatter, you know, if you scatter on a nucleus, it has many nucleons inside. And what this formula essentially is telling you, that the leading scattering process will be between a dark matter and let's say one nucleon line, and then all the other nucleon lines, nothing will happen to them. Okay, there are more nucleons in the nucleus, and there will not be there. You know, you could have a diagram where you have like lots of pions that connect all these pieces, yeah, in complicated ways. Something like this. But if you use this formula, you see that this diagram is much more suppressed. Okay, so I don't know if this is a good explanation.
No, that helps for sure. Sorry to belabor the point.
Yeah.
Thanks.
Yeah. So, you know, there could be like there could be other things going on in this nucleon, like there could be pion exchanges here in some way, but this one will be more suppressed than just not considering them. Okay. And now, and now what you see is so first of all, for a given number of for a given type of interaction, first of all, again, you see that you should minimize the number of loops. So again, tree level will be most important. And then you can compare processes with nucleons and without nucleons. So by like setting this ni to 0 or not to 0. And then you can just decide for a given interaction which diagrams are leading. And for now, if you look at the one example that we discussed, the exchange of a pseudoscalar, we have seen that the interactions that we have that do not, okay, how to say, the interactions where the dark matter directly interacts with a nucleon has somehow this form. Yeah, there's no contact interaction between just the dark matter and the nucleon, because this is a pseudoscalar interaction, so there must be another pion. So now what do you do with this pion? So you can take this pion and make a loop out of it. Okay, but then you pick up a factor of 2 here. Okay. But we have also seen there are also interactions for a pseudoscalar interaction. There's just an interaction with just a single pion. And this pion can interact with the nucleon here. And now if you just calculate this power nu here, then you will see that this nu is smaller than this nu. Okay, so you see that this one is the leading interaction. And in this case, there's just this for pseudoscalar, this one doesn't exist. For pseudoscalar. Okay, so that's how you would use this formula. Maybe another example. An example that I didn't discuss, but that's also kind of important. Another example. let's look at this interaction. So that's just an axial vector current. This would be the leading interaction if you have a Majorana dark matter particle, so and like a neutralino or something in SUSY. It doesn't have vector interactions, so it can only have axial vector interactions. And if you do the same analysis using this power counting formula for this interaction, you will see the following. There are two types of diagrams. So now you can actually have this contact interaction. And you can also have this one with a pion exchange. And in this case, it turns out that they are of the same order. Okay, so in this case, they give the same power nu, so the same power of q, and you have to include both of them. And there will be actually, yeah, okay, depends on the model, but typically there's an interference between them, which is negative. So if you include this diagram, the cross section will get smaller than what you would naively expect. Okay, so that's another example where pions contribute. Yeah. Or you can ask the question maybe, what about such interactions, a dark matter that interacts with two nucleons at once, something like this. And if you analyze this using this power counting formula, you will see that this always suppressed by 3 powers of q over m. So that always goes like the leading diagram plus 3. So that's always down by q over m to the power 3. And then, I don't know, so then kind of, you can just play with the possibility. So then there you can have something like this, a dark matter particle that interacts with 2 pions and it couples to a nucleon or something via loop, or maybe the pions just connect to 2 different nucleons, something like this. And in this case, it depends again on the type of interaction. And sometimes the suppression is by additional 3 powers. And I think that, so it's never of the same order, but sometimes the suppression is only q over m. Okay, and this is like numerically q over m is something like 30%. So if you're interested in 30% effects, sometimes you have to take into account either loops or interactions with 2 nucleons. But this happens only for very few interactions, and I've listed them in the lecture notes. I don't now remember exactly which ones. But it's written in the notes if you're interested. Okay. Yeah, so that's how one works with these chiral interactions. Even if it's non-perturbative, there's kind of a systematic expansion, and you have a very clear strategy of like which terms to include and which terms not to include. And okay, I should maybe also say that this gives you kind of the overall scaling of the diagrams. And then of course there can be coincidental factors or factors given by your model that multiply these scalings. So if you're unlucky and there's a term that's suppressed by 1 power of q over m, but it comes accidentally with a large factor in the model, then you have to take it into account. But generally speaking, this gives you the picture of what is happening. And the picture of what's happening is that typically interactions with 1 nucleon dominate. And for some interactions, the pion exchange contributions dominate. And this typically happens if there's an axial vector or pseudoscalar dark matter interaction. Okay, so now I talked a lot. Maybe I should ask if there are any questions or like anything else that you would like to know.
Yeah, so this VI that you have, sorry, I think I got a little lost with some of the lettering. This VI is the total number of vertices, or what is this exactly?
Sorry, could you repeat the question slowly? I didn't understand.
Yeah, what is V sub I?
D sub I, that's the number of derivatives.
V
for example, so you're talking about this one.
V as in Victor.
V. That's just the type of vertices, because you might have different types of vertices. So for each, you might have one vertex with one derivative and two vertices with two derivatives. So that's the number of vertices with these properties. That makes sense. So
yes, it does.
Yeah. Okay.
Also, is there a qualitative way to understand why the nucleon line and pion line scale differently with Q?
Why which ones scaled differently? Which one?
Why the nucleon line and the pion line?
The nucleon line and the pion line? Good question. I think the reason is, let me see. I mean, first of all, the nucleon is a fermion, is a spin 1/2 particle. The pion is a spin 0 particle, and we treat the and the nucleon is heavy. So I think that the essential thing that is happening is that in the denominator, this p² piece cancels against the mass piece. So kind of the leading term is just the p.q. I don't know if I have a good intuitive explanation for this. That's just what comes out if you do. That's just that's the typical propagator of a non-relativistic field.
Is the idea kind of like if you have a contact interaction between the dark matter and the nucleon probably won't recoil much because it has a large mass, but if you have a contact interaction between a dark matter and a pion, the pion will recoil more and therefore scales like 1/q².
Yeah, if you exchange a pion, then this will scale like 1/q². Yes.
Okay, thank you.
Yeah, exactly, and that suppresses the momentum dependence. Yeah, that's one way to see it. Yes, any more questions? Or anything that we should discuss again, or?
Yes, we're getting here.
Yeah, so yesterday we talked about charismatic propagation theory. I was wondering if you could, I don't know, expand a bit on this relation you came up with, this n⁵² and q, how they relate. I think at leading order.
Yes, which relation? Which relation are you referring to?
The one that n⁵² scales as nq.
n⁵² scales as n. That's is that correct? You're asking about this relation, n⁵² is proportional to nq? Okay. Yes. So, okay. So yes, I can say something about this. So first of all, what are masses in a formal way? Masses are so if you write down the Lagrangian, then the coefficients of any terms that are bilinear in the fields are the masses. So like a quark mass term looks something like this, minus q bar mq. So I've seen, so that there are two fields here, anti-quark quark. And for pions, the mass terms will look something like this, m pi squared times, I don't know, pi 0 squared, or pi plus, pi minus. There might be a factor 1/2 here, maybe. Okay, so that's first of all, that's kind of our definition of what we mean by masses. And why are the two related? Okay, so first of all, that's just by how we construct the chiral Lagrangian. So we first of all, we write the mass term as q bar left and q right plus Hermitian conjugate. And then we say, okay, and we do this Boolean trick. So we give this MQ a formal transformation property that goes like VL MQ VR dagger. And then we write down a invariant term in the chiral theory that has the same invariance property, and that's let's call it L mass, some constant, it's not so important, divided by, let's see, where is it? 2 trace MQ U plus U dagger. Okay, so how do you write down this term? That's just from symmetry arguments. Okay, that's just the term that has the same transformation property as this term. Okay, B is just a constant that needs to be calculated by lattice. Let's say F is the pion constant. So these are just numbers. And then now this is a complicated function of the pion fields, but remember that U was just given as the exponential of I times pi, I don't know, divided by F or something, and square root 2 or something like this. So U equals 1 plus I square root 2 pi over F plus higher order. So you can just expand this. So these are 3 by 3 matrices. You expand them in this way, you take the trace. So this gives like an enormously complicated expression, but some of these expressions will have terms that are bilinear in the pion fields. I don't know, B0, let's say some number times pi plus pi minus. And this number, because there's and there's this quark mass matrix here. So this will actually look like this times some number. Okay, and then from this you just read, so this is the pion mass term. So I think there will be a B0 here. Okay, sorry, it's slowly coming back to me what it should be. Some number times B0 times MQ. And from this you just read off that the pion mass squared, that's just by definition the pion mass term, and it's linearly proportional to the quark masses. So you see, if the quark masses vanish, then the pions are massless, and this relation is linear. Did this answer the question?
Yeah, thanks.
Okay, very good. Yeah. It's kind of nice because experimentally this gives you a possibility to determine, you can't really determine the quark, like purely experimentally, you cannot really determine the quark masses from the pion masses because you need B0. If you calculate this on the lattice, you can read off the quark masses in some sense. But if you take ratios of pion masses, then this B0 will drop out. And then, if you, for example, from the ratio of mk over m pi, you can somehow get, okay, that's a bit simplified, but you can get somehow the ratio of the strange mass over the up and down mass. Okay, again, just a side remark. Yeah. More questions?
I don't see any here for the moment. Anyone wants to raise some point? On Zoom? No, I don't think so. Yeah, one.
Since we have a couple minutes here, just out of curiosity, what are the beyond the standard model mysteries that most spark your interest? What do you think is like the most curious?
Yeah, very good question. I don't know if I have like a favorite model or puzzle. I mean, one thing that I find interesting to follow is the mu on G-2. Has nothing to do now with dark matter. I don't know, my background is in flavor physics, so I like to follow the flavor physics anomalies and like to make predictions about. I mean, what I'm recently mainly working on is actually CP violation in kaons. I don't know. I mean, of course, I mean the elephant in the room, dark matter, of course. What is dark matter? That's a very interesting question. I mean, the hope is we find out somehow. I think we need more experimental input, clearly, to say more. What else? I'm interested in the baryon asymmetry of the universe and new sources of CP violation. Yeah, that was your question. Just what personally, what is interesting to me.
Yeah, so that sounds like an interesting list, a good one. So I don't know if there is nothing else we want to discuss with Joachim. I think that's it. So thank you very much, Joachim, for your availability and your speak and be here for us. Thank you.
Yes, thanks to all of you for attending the lecture and the discussions and for the good questions. And you know, if you have any more questions, since I'm not around, unfortunately, but if you want to ask more, if you want to discuss, just send me an email, and I'll be happy to answer or to like even talk if you want.
Let's hope to see you in person next time. Thank you.
Yeah. Thanks. Bye bye.